Ahoy mateys, time for some polynomials. The definition of a polynomial is that it has the form a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus and so on and so forth all the way down to a sub 1 x plus a sub 0. So in this, for this to be a polynomial, right, all the powers have to be integers and they have to be at least 0. So they have to be nice whole numbers, basically. It can't have any fractions, so x can't be in the denominator, hence no negative powers. And because all the powers are nice whole numbers, no roots with x inside. So thanks to all of those nice things, all of the coefficients are real, all of the x's are nice. Thanks to all of these things, the polynomials graph is a nice smooth curve. There's no holes, there's no jumps, there's no elbows. It's just a nice smooth curve for the whole length of its domain, which would be all reals. So that's the nice piece about a polynomial. It's going to be pretty in a lot of ways, mathematically anyway. And so we're going to work with those for a little while. Now, we're still dealing with possible transformations, and we have some more base functions that we might want to deal with. Those in polynomials are power functions. So an even power function is going to look like f of x equals x to the n, where n is even. These will be symmetric to the y-axis. Think about x squared, right? We know that's symmetric to the y. It's the same thing here, even if it's to the 4th or the 6th or the 24th. All of those are symmetric to the y. All of them have a domain of all reals. All polynomials will. The range, though, for a base function like this one is that y will be at least 0, it'll be greater than or equal to 0. So it'll have a turnaround there at 0, 0, and that'll be the lowest it goes. The base points are negative 1, 1, 0, 0, and 1, 1. It may help to add a 4th base point here, 2, 2 to the n, whatever that power is in this case, just to give you some other idea of like how stretched it looks. And this is a graph of x to the 4th. So that'll be the general shape of them. The higher the power, the more of a bucket it looks like. So the bottom will flatten out a little bit and get fatter, and the sides will go up faster, right? If we think about raising 0.5 to the 4th, we're going to get a really small decimal, right? So until we get to 1, we have really, really small y values. And then when we get to 1 on the x, all of a sudden 2 to the 4th is huge. It's 16. So the higher the power, those will go up faster. So now if we have even, we obviously need to have odd. The base function looks the same, only this time n will be an odd number, 3, 5, 7, 9, etc. These functions will be symmetric to the origin. If you think about x cubed, right, we know it kind of does this. And so we're looking at that symmetric to the origin. Again, the domain is all reals. Now the range is all reals as well, right? We're starting at the bottom and coming to the top. The base points are negative 1, 0, 0, and 1, 1. Again, it might be helpful to throw in a 4th base point of 2, 2 to the n, whatever power that is. And it looks like that x cubed function. I think this is x to the 5th. I can't remember if I used x to the 1st or the... I can't remember if I've used x to the 3rd, or x to the 5th. So there are different properties of polynomials we might want to know. So this is one not well drawn, but here's a polynomial that we have. The x-intercepts are going to be each of the r's. R1, 2, 3, and 4 are the 4 x-intercepts. They can also be roots, or called roots or zeros. And for an x-intercept, we know, or told, that f of that root equals 0. Right, that would make sense. Our y value is going to be 0 from those x values. And that means that this expression, x minus r, is a factor. When we talk about x-intercepts, though, we tend to want to talk about this multiplicity. And that's the power of the factors. So if you have x minus 2 cubed, that has a multiplicity of 3. If you have x minus 1 to the 1st, that's a multiplicity of 1. and that's the power that it's raised to. It's essentially the number of times that that's a root. If the multiplicity is even, then the function touches of that root. So this has an even multiplicity, and if it's odd, it crosses. So the other three have odd multiplicities. The y-intercept is f of 0. This would be your y-intercept here. And when we're talking about a polynomial, we tend to want to talk about turning points. Turning points are places that it turns around. There are going to be, at most, n minus 1 turning points, where the highest power of x is n. So if we have a cubic that we're dealing with, then we're going to have at most 2 turning points. We could have none. That doesn't happen often, but if you look at x cubed, it doesn't have 2 turning points, it has 1. But not even really that, it has none. It just kind of comes up, flattens, and keeps going. If you think about x squared, though, that has 1 turning point. So we can have at most 1 less than the degree for turning points. And then the other piece that we want to talk about is end behavior. End behavior is describing what the graph is doing as x goes to positive infinity and negative infinity, these really far extremes. This is based on the power function that leads it. It's based on the highest power of x in that polynomial and its coefficient. That first term is going to take over. If you think about putting 2 to the 4th, and then 3 to the 4th, and then 4 to the 4th, it's not going to compare to the other pieces that when we get to these bigger numbers, it's just going to take over. So when you're putting in 100 and when you're putting in 1000, that leading term is going to be deciding where we're at for the most part, right? Like the other pieces just won't be as big. So we're going to base it off of that term. So if that leading term, a sub n x to the n, is positive and n is even, it opens up. If it's negative and n is even, it opens down. We should expect this right from transformations. If it's positive and odd, then it starts at the bottom and ends at the top. If it's negative and odd, then it starts at the top and ends at the bottom as we go left to right. Yes, left to right. So those are the things we generally want to determine about a polynomial in order to be able to graph it. The x-intercepts, the y-intercept, the turning points, and the end behavior. What's it doing? And then we can kind of connect the dots. So we'll do that. We have a polynomial here. It is f of x equals 4 times x plus 4 times x plus 3 cubed. So we're going to list each real zero with multiplicity. So if we have the factors, then we have the zeros. X equals negative 4 and x equals negative 3. Those are the two zeros here. What are their multiplicities? Well, negative 4 has a multiplicity of 1. Its factor, its parentheses, is not raised to any power, so that's an implied 1. Negative 3, though, is raised to the third, so its multiplicity is 3. So then we're asked, does the function cross or touch at each zero? Well, it's going to cross at both. Both 1 and 3 are odd, so therefore it crosses. If it had been even, it would touch, right? Okay. What's the end behavior? This is a little bit harder to do. When it's not already factored, when it is already factored for you, this makes it much more difficult because we have to actually do the foiling out. But we don't have to foil the whole thing. This piece is gonna, if we multiply all that out, is gonna give us x cubed. This is gonna give us x as the biggest power, and this is just 4. So if I multiply those together, multiply out this is going to be an x cubed, multiply this out, it's just going to be an x, and multiply this out, it's going to give me a 4. When I multiply all three of those things together, I get 4x to the 4th. So the end behavior is 4x to the 4th. And I have a tendency to make it look like that. We're going up and up. Maximum number of turning points. Well, if the highest degree is 4, the max number of turning points is 3. And then we need to sketch it. Now here's a couple of tricks about sketching these. First of all, we know where our intercepts are, so we know the important pieces. Second of all, let's not do extra work that we don't have to do, right? So if I draw in my axes, so now I have 1, 2, 3, 4, 5, 6. Okay, so here's -6, -4, -2. All right, and we know we have a dot. We'll change colors so it's easier to tell. We have a dot at -4 and a dot at -3, and we know the end behavior is up and up. So this graph should look something like that. Now, is that perfect? No. Maybe it does some more of that W-ness right in the middle. We don't know. We haven't looked at it. So here's where I say, okay, use the points you know. I know my intercepts, and I know my end behavior, so I really know what's going on. And then grab your calculator, or go to Desmos, or something, and get a good look at it. Okay, so on my graphing calculator, it actually looks like it does something more like comes down, comes up, and flattens out there. It looks kind of like that to me. That's not a great drawing of it, but that's the idea. Does it need to be perfect though? No. I'd like you to have looked at it and kind of figured out what it's supposed to look like. Maybe you change your Y scale, not your X's usually, because those are usually good. But change your Y scale so that you can see more of it, see more of the shape that's going on when that's possible. But we should get a graph something like this. I'm going to be looking for, is your end behavior right? Are your intercepts right? Does this make sense? Note that I haven't scaled the y-axis at all because I haven't hit the y-axis. I don't know where this point is exactly. I have no idea where that is, and without calculus or my calculator, I won't know. So it's not important. What's important is the shape. What are you getting as an idea of this function when we start? Also note that I don't have a y-intercept on here because it's probably huge. It's going to be 4 times 4 times 3 cubed. So 16 times 27, it's going to be giant. I'm not going to label that. I can't draw that. So don't worry about it. I've hit my 2 x-intercepts. I wasn't asked about my y-intercept. I can continue. Okay. Here's our second example. You get to do this one. Fill out each of these questions. Pause it here. Come back. Welcome back. How'd it go? Let's see what I got. The zeros, I got 0 with multiplicity 1 and 3 with multiplicity 2. That x squared plus 4 didn't give me any zeros. Yes, it has a multiplicity of 3, but it didn't give me any roots, so we leave it alone. Cross or touch? 0 crosses, 3 touches, because 3 has an even multiplicity. Again, we're not dealing with that x squared plus 4 term. But now when we talk about end behavior, that's where it becomes important. So if I take 2x times x squared times x to the 6th, right, x squared cubed, we're going to multiply, raise a power to a power, we multiply. X times x squared times x to the 6th gives me x to the 9th with a leading coefficient of 2. So it's positive odd. That means it's going to start at the bottom and end at the top as we move left to right. What's the maximum number of turning points? 8, because the highest power of x was 9. And then I get this graph. Is it perfect? Again, probably not. This x squared plus 4 all cubed term is going to definitely change the shape going on here. But my y-intercept is 0, so I don't have to scale the y-axis, and so I can make it look about like this, and I have got the idea down. Okay, that's not all we have to do with polynomials. Sometimes we have to work backwards. We want to find the equation of a polynomial with zeros -3, -1, 2, and 5. 5 has a multiplicity of 2, and the function has a degree of 5. Why do they tell us this part? Well, this degree of 5 part, it tells us that there aren't any more roots. I don't have to increase the multiplicity of any of these. I'm given everything I need. So if x minus 3 is a 0, x plus 3 is a factor. If -1 is 0, x plus 1 is a factor. If 2 is a 0, x minus 2 is a factor. And if 5 is a 0, x minus 5 is a factor. And this has a multiplicity of 2, so I'll put a little squared up there. And that's it. Now I have an equation of a polynomial. All the powers will be nice. All of the coefficients will be real. I have not broken any rules as far as my polynomial rules, what constitutes a polynomial. So we're done. Do I want to fill this out? No, I don't want to fill out a 5th degree polynomial. You can, and if you do it, I might follow your work and do it with you, or I might do it on my own, but sometimes I just skip it. It's a lot of work to foil this out, so leave it. This is good, and this actually gives us more information than the whole foiled out one would give us on first glance. So this actually is beneficial. So now do the same thing with this one. You need to find a polynomial that fits this graph. You have the intercepts, and they're all odd, right? So they could all be power 1, but that y-intercept means you might have to sub in a point and solve for some a value, some scaling value, or maybe it needs to be flipped or something. So this is where we legitimately guess and check. We start with stuff, see if it works. If it doesn't, try again. So try that out. All right, did you try? Did you get stuck? It's okay to get stuck. It's good to ask for help. So let's see. We know that x plus 1 is a factor. So is x minus 1 and x minus 2. But when we sub in 0 to this for x, I get 1 times -1 times -2, which is 2. This is not 2. So I need a scalar. So that's where I put in an a. Y equals a times x plus 1, x minus 1, x minus 2. And with all those in, I can sub in my point. -1 equals a times 0 plus 1, 0 minus 1, and 0 minus 2. It's supposed to be a 0. There we go. And I can FOIL. This gave us 2a equals -1, so a is -1/2. So my scalar, right, to make this flip over and be a little bit shorter, I need a -1/2 in front. So my function is -1/2 times x plus 1, x minus 1, and x minus 2. Is that a process that kind of makes sense? We've done this before, right? We did this with quadratics. We had the vertex and we had another point and we used that to find a. Same idea here. All right. So as we go to do problems, the way to show me that you've actually learned like what a polynomial is and how to deal with one is to work on graphing it. So to graph one, you have 5 steps. I think there's 5. You have several steps. Determine the power function that describes the end behavior. Remember to use that leading coefficient, so that -1/2 matters a lot in that last example, right? Then find all the x-intercepts with their multiplicity. Also find the y-intercept. It may not be super helpful, but it might be helpful. It might be a nice, easy number, so pay attention to that. And then determine whether the function is crossing or touching at each x-intercept, because that's important for when you're connecting your dots, right? The optional step here is determine the maximum number of turning points. This doesn't necessarily help you a whole lot, but it's good to know that I shouldn't be turning around more. Can't be creating more W's in there than there actually could be. And then sketch the graph. Use your calculator to check your work. I definitely recommend that. If you type the original function in before you did anything to it, if you type the original into your calculator and graph it, whether that's on your computer or your calculator or whatever, that's going to give you a good idea of if you did something wrong somewhere along the line. So grab your calculator and check your work. That's going to make your life a lot easier. So in this section, you might see something like cubic reg. We have done linreg, a linear regression, and we've done quadreg, where we fit a quadratic. So now we can fit a cubic. We're just moving up. If you're given data, treat it like you have been, just fit a cubic function, use cubic reg in your calculator. Remember that transformations are still hugely applicable, and we'll just be using our new power functions. And so when we start looking at something in maybe kind of a vertex form, maybe we'll see something like f of x equals 2x minus 3 cubed plus 1. We don't want you to FOIL that out and figure it all out. We want you to use that and say, okay, this is x cubed, moved right 3, up 1, and stretched, right? We still want you to use the transformations that we know. And finally, know that your graphs don't have to be perfect, but there are specific details that everybody's going to be looking for. Where are your intercepts? Are those correct? What's your end behavior? Is that in the right direction? Multiplicity also is important so that we're touching or crossing in the right places. So pay close attention to those, and then don't stress if your graph isn't quite as pretty as your neighbors, or if you didn't go quite as high with your loops as somebody else. That's not a huge deal. As long as you didn't label your y-axis too much, you're probably fine.